Beyond Neptune, where the sun no longer feels like a sun, the solar system begins to loosen into darkness. The light out there is thin and old, spread across frozen plains, red ice, silent craters, and small worlds that move so slowly they seem almost still. These are not planets in the familiar sense. They are leftovers. They are cold records of a time when the solar system was still taking shape, before drifting deeper into that outer dark. Take a moment to settle in. If this quiet journey through Pluto, Charon, Makemake, Quaoar, Sedna, Orcus, and the first star beyond the sun is the kind of space documentary you enjoy, you can subscribe, leave a like, or share it with someone who likes falling asleep under distant starlight. And if you feel like leaving a small trace behind, write where you are listening from and what time it is where the night has found you. Maybe the room is dark already. Maybe a fan is moving softly somewhere nearby. Maybe the screen is dim, the blanket is warm, and the day is finally beginning to loosen its hold. Let the details come slowly. There is no need to remember every number, every name, or every frozen orbit. The outer solar system does not rush. Its worlds have waited for billions of years in faint light, carrying their old surfaces through the cold. The path begins with the best known of them, the small world that once stood alone at the edge of every schoolroom map. Pluto is not the end of the solar system. It is the first clear doorway into the deep belt of ice beyond Neptune. Pluto moves through a part of the solar system where sunlight has almost lost its warmth. From Earth, the sun is large enough to define the day, to cast sharp shadows, to warm stone and water and skin. From Pluto, it is still the brightest object in the sky, but it no longer rules the landscape in the same way. Its light arrives thin and delayed, spread across ice that has not known an ordinary sunrise for billions of years. The horizon there is not blue, it is black. Even at noon, stars remain visible above the surface, and the sun hangs among them as a hard white point, bright, distant, and strangely small. For a long time, that was nearly all Pluto could be from Earth. A point of light, moving slowly against the background stars. It was discovered in 1930. After years of careful searching for something beyond Neptune, the object was so faint that it did not announce itself as a world. It shifted slightly from one photographic plate to another, a quiet displacement in the dark. That tiny motion was enough. A new body had been found at the edge of the known planetary system, and for much of the 20th century, Pluto carried the idea of the final planet, the last named stop before the cold grew formless. The truth turns out to be stranger and more gentle. Pluto is not an ending. It is one member of a wide outer population, a belt of icy objects left from the earliest building of the solar system. It is smaller than Earth's moon, smaller even than several moons around the giant planets, yet it is large enough to hold a shape, a skin, seasons, mountains, plains, a thin atmosphere, and perhaps a hidden sea. It is not a simple frozen stone. It is a small world, active in ways that were not expected, carrying its age and its motion through darkness. Its path around the sun is stretched and tilted, unlike the nearly flat, nearly circular paths of the inner planets. Pluto does not keep to the main road. At some parts of its orbit, it comes closer to the sun than Neptune does, though the two bodies never collide because their motion is locked into a stable rhythm. Neptune circles the sun 3 times while Pluto circles twice, a gravitational pattern that keeps distance between them across vast spans of time. Pluto's year lasts 248 Earth years. Since its discovery, it has not yet completed even one full circuit around the sun. That single fact changes the feeling of the place. On Earth, generations pass while Pluto is still moving through one season of its long orbit. Its surface does not experience change quickly. The sun brightens by small degrees over decades, then fades again over centuries. Frozen gases loosen when Pluto is nearer the sun and settle back when it travels outward. Nitrogen, methane, and carbon monoxide do not behave there the way they do on Earth. On Pluto, they are part of the ground. They can freeze into plains, flow slowly like glaciers, rise into a thin atmosphere, and fall again as frost. The first close look comes from New Horizons, the small NASA spacecraft launched in 2006. It leaves Earth at high speed, passes Jupiter for a gravity assist, and spends years crossing the widening dark beyond the giant planets. During that long passage, Pluto grows from a point into a world. The spacecraft does not stop there. It moves too fast and carries too little fuel for orbit. It performs a flyby, a brief encounter, after a journey of 9.5 years, passing through the Pluto system in 2015 and sending its data home across billions of kilometers. The encounter is brief, but the return is slow. The signal takes hours to cross the distance, and the data arrive at Earth over many months, little by little. Images appear one after another, each one replacing an older idea of Pluto. The brown blur seen by distant telescopes becomes a landscape with a heart-shaped plain, dark equatorial regions, high icy mountains, craters, troughs, haze layers, and surfaces that look young beside surfaces that look ancient. Pluto is not uniform. It has memory written into it, and that memory is uneven. The most visible mark is Tombaugh Regio, the large, bright area shaped roughly like a heart. It lies near Pluto's equator and covers a broad portion of the visible hemisphere. Its western lobe is Sputnik Planitia, a pale basin filled mostly with nitrogen ice. The plain is smooth compared with the lands around it. It holds few obvious impact craters, which means its surface has been renewed in geologically recent time. On a world so cold and so small, that is not an ordinary thing. It suggests motion. Sputnik Planitia is not smooth because nothing has happened there. It is smooth because something continues to happen slowly. The nitrogen ice appears divided into broad polygonal cells, each one tens of kilometers across. Their edges are marked by shallow troughs, dark seams, and clusters of small hills. The pattern resembles convection, the same physical idea that makes warm fluid rise and cooler fluid sink. Although here the moving material is not liquid water in a pot. It is frozen nitrogen, warmed faintly from below, flowing over immense periods of time. The movement is slow beyond daily understanding. A human lifetime would not see the plane change as a river changes, but Pluto has time. Beneath the pale surface, nitrogen ice can soften and creep. Warmer material rises at the centers of the cells, spreads outward, cools, and sinks along the borders. The result is a living texture on a world once imagined as dead. No volcano has to erupt. No sea has to break open. The plane can renew itself by a nearly silent circulation of frozen air turned into ground. Around Sputnik Planitia, the terrain rises into mountains made largely of water ice. On Earth, water ice is fragile compared with rock. It melts under the sun, cracks under boots, and floats in winter ponds. On Pluto, water ice is stone. At temperatures more than 200 degrees Celsius below zero, it becomes hard enough to build mountains. The ridges called Hillary Montes and Tenzing Montes stand along the edge of the bright plain, their walls and peaks rising from the surrounding landscape like broken blocks pushed upward and left in place. Those mountains tell part of Pluto's story. Nitrogen ice is too soft to hold tall peaks for long, but water ice can. The outer shell of Pluto is not made of one simple material. It is layered and mixed, with stronger water ice forming the bones of the landscape and softer volatile ices spreading over lowlands and basins. Methane frost may brighten ridges, carbon monoxide may gather in colder places. Nitrogen may drift and flow. The surface becomes a map of temperature, sunlight, gravity, and time. The heart-shaped plain may sit inside an ancient impact basin. Long ago, a large body may have struck Pluto and carved out a depression wide enough to change the world's balance. Later, nitrogen ice collected there, making the basin heavier. The weight of that frozen mass may have helped turn Pluto's outer shell, slowly reorienting the world so that Sputnik Planitia settled into its present position. A collision, a basin, a load of ice, and the turning of a small planet across deep time. Nothing moves quickly, yet everything matters. There is also the question of what lies below. Pluto is small, and small worlds lose heat more easily than large ones. For that reason, it once seemed natural to imagine its interior as completely frozen, but New Horizons changed that assumption. The shape and location of Sputnik Planitia, the patterns on the surface, and the way the crust may have responded to stress all leave room for a hidden ocean beneath the ice. Not an ocean like Earth's seas, open to air and light. A dark internal layer, probably salty, probably mixed with ammonia, sealed beneath a thick shell. Nobody knows yet whether that ocean exists today in liquid form. The evidence points toward the possibility, not a final answer. If it is there, it survives because chemistry and pressure can lower the freezing point of water, and because some heat may remain inside Pluto from the decay of radioactive elements in rock. The ocean would have no waves under a sky. It would never reflect stars. It would be pressed between ice above and rock below, silent and black, hidden under one of the coldest surfaces ever visited by a spacecraft. That possibility changes the meaning of Pluto, a place at the edge of the solar system, receiving weak sunlight and moving through a long winter, may still contain an internal boundary where water and rock once interacted, and perhaps still do. It does not make Pluto Earth-like. It does not make it alive. It simply means that the outer solar system is not only a graveyard of frozen remnants. Some of its worlds may have interiors that kept changing after their surfaces fell into cold. Away from Sputnik Planitia, Pluto grows darker. East and west of the bright heart, wide regions show older ground, more impact craters, rougher surfaces, and red-brown coloring. The largest of these dark regions is Cthulhu Macula, stretching across a huge portion of Pluto's equatorial zone. It absorbs much more light than the pale nitrogen plain beside it. The contrast is sharp. A bright frozen basin next to a dark old belt, like two ages of the same world placed side by side. The dark color likely comes from tholins, complex organic molecules formed when ultraviolet light and charged particles alter simple ices such as methane and nitrogen. Tholins are not life, they are chemistry. They form reddish, brownish residues that settle onto cold surfaces and slowly tint them. Across the outer solar system, that red color appears again and again on Pluto, on many Kuiper Belt objects, and on worlds so far away that sunlight is only a dim source of chemical change. It is a color of exposure. It shows where simple frozen gases have been worked by time. Cthulhu Macula is not smooth like Sputnik Planitia. Its surface is mixed with plains, craters, mountains, and uneven rises. Some parts appear heavily marked by impacts, which means they have not been renewed in the same way as the nitrogen basin. Other parts are shaped by frost and relief. Pluto is small enough that every major region seems personal, almost like a separate record. The bright plain says motion. The dark belt says age. The mountains say strength. The haze says air. That haze is one of Pluto's quiet surprises. Pluto's atmosphere is extremely thin, mostly nitrogen with small amounts of methane and carbon monoxide. It is nothing like the dense air of Earth, and it would not support clouds or weather in the familiar sense. Yet it exists. Sunlight breaks apart methane high above the surface, leading to chemical reactions that produce fine particles. These particles form layered haze, rising hundreds of kilometers above the ground. In images from New Horizons, the haze appears as delicate blue bands around the dark limb of Pluto. Blue is not the color expected from such a cold, distant world. The particles themselves are probably reddish or grey when they settle, but they scatter sunlight in a way that gives the upper atmosphere a blue cast. It is a thin color, almost fragile. Around a world of nitrogen plains and red organic frost, the atmosphere draws a faint outline, letting Pluto appear not as a bare object, but as a body wrapped in a vanishing skin. The atmosphere also changes with the seasons. As Pluto moves nearer to the Sun, more surface ice can sublimate, changing directly from solid to gas. As Pluto travels outward, the gases can freeze again and fall back onto the surface. For years after Pluto's closest approach to the Sun, scientists expected the atmosphere to perhaps keep growing for a while, because the surface still held warmth from earlier sunlight. Later observations suggest that parts of it may now be cooling and settling. The air of Pluto is not stable in the way Earth's atmosphere feels stable. It breathes over centuries. At the North Polar regions, sunlight can linger for long periods because Pluto's axis is strongly tilted. Long seasons expose one pole and then the other, allowing frost to migrate across the globe. Nitrogen may leave one region and gather in another. Methane may brighten highlands. Darker terrain may warm slightly more than lighter terrain, changing where volatile ices remain and where they disappear. The result is a world painted again and again by weak sunlight, not in days, but in eras. The surface is not only cold, it is responsive. It answers faint changes in light with movement so slow that the word weather almost becomes too quick for it. On Pluto, weather can become geology. Air can become ground. Frost can become terrain. A basin can fill, press downward, and perhaps help turn the crust of the world itself. The boundary between atmosphere and surface is not fixed. It shifts as Pluto follows its long path, drawing a thin veil around itself, then letting that veil fall. In the southern regions seen by New Horizons, there are signs that may point to cryovolcanic activity. Some features appear like broad rises or collapsed structures, too large and strange to be easy impact craters. Right mons and nearby terrain have been discussed as possible cryovolcanic constructs, places where icy material may once have pushed upward from below. The word volcano brings to mind molten rock, red light, and heat. On Pluto, the idea is colder and slower. The erupted material would be water-rich ice, ammonia-rich slush, or some other mixture able to move before freezing into the shape of the land. This is still uncertain. Pluto's surface leaves clues, but not all clues lead to one answer. Some shapes may be formed by collapse, some by uplift, some by the motion of volatile ice, some by ancient impacts blurred by later processes. The honest picture is not simple. New Horizons saw one hemisphere in detail during a fast passage. Much of Pluto remains less clearly mapped. A spacecraft passed once, looked hard, and moved on. That single flyby makes every image feel temporary. There is no orbiter circling Pluto day after day, watching frost move through the seasons, measuring the atmosphere as it thins and thickens, mapping the far side in equal detail. There are only the data gathered during the encounter and later observations from distant telescopes. The rest must be reconstructed patiently. Pluto is known better than before, but still not fully known. It has become clearer without becoming ordinary. The spacecraft itself continues outward after the encounter, carrying the memory of Pluto into the Kuiper Belt. Behind it, the dwarf planet keeps moving around the Sun. The bright plane continues its slow overturning. The dark regions continue to gather the chemical residue of weak light. The mountains of water ice remain hard under the black sky. The haze rises and falls in faint layers. If an ocean is present below, it remains hidden, sealed away from the stars. Pluto is often remembered because it lost the title of planet. That story is small compared with the world itself. Names and categories change because human understanding changes. Pluto did not change in 2006. It kept its tilted orbit, its nitrogen glaciers, its red ancient plains, its thin air, its locked companion Charon, and its place among the icy bodies beyond Neptune. The change happened closer to home, in the way the solar system was organized in human language. Seen from far away, that argument fades. Pluto becomes what it has always been, a small, active, frozen world at the entrance to a wider region. It is not alone. Beyond it and around it, countless bodies move in darkness. Some large enough to be round, many no bigger than mountains, all carrying pieces of the same early history. The old map ended at Pluto because the dark beyond was hard to see. The newer map begins there. The path now turns toward the companion that makes Pluto stranger still. Charon is not a small moon circling quietly at a great distance. It is large enough to pull the center of motion outside Pluto itself. The two bodies face one another across the cold, locked together by gravity, each keeping the same hemisphere turned toward the other. Pluto's bright heart and dark plains are only the first half of the system. The other half waits nearby, grey, scarred, and marked at its pole by a stain the color of old frozen chemistry. Charon hangs close to Pluto, large enough that the word moon begins to feel incomplete. It does not circle Pluto the way Earth's moon circles Earth, with one body clearly central and the other clearly secondary. The balance is different here. Pluto and Charon move around a shared point in space, a center of mass that lies outside Pluto's surface. In the dark beyond Neptune, the two worlds do not form a planet and a small attendant, they form a pair. Their distance is small by the standards of the outer solar system. About 19,000 kilometers separate their centers, less than the width of many planets. Across that gap, gravity has worked for billions of years, slowing their rotations until each keeps the same face turned toward the other. From one hemisphere of Pluto, Charon never rises and never sets. It remains fixed in the sky, a grey disk suspended above the same lands for age after age. From the opposite hemisphere, it is never seen at all. The same is true in reverse. A person standing on the Pluto-facing side of Charon, if such a surface could be stood upon, would see Pluto hanging in one part of the sky, far larger than Earth's moon appears from Earth. Pluto would show phases as sunlight shifted across it, but it would not drift from horizon to horizon. It would stay. It would be a constant presence above a cold, scarred landscape. Its bright heart and dark equatorial plains turned outward across the gulf. That locked stillness is not the absence of motion. Both bodies are moving constantly, turning around their shared center every 6.4 Earth days. The system is like a slow dance in which neither partner lets go and neither turns away. The motion is regular, quiet, and old. It is also one of the reasons Charon matters so much. Its size is not a detail. Charon changes the whole geometry of Pluto's world. Before spacecraft saw it clearly, Charon was itself only a slight distortion near Pluto. It was discovered in 1978, when careful observation showed that Pluto's image was not quite symmetrical. A small bulge appeared and disappeared as the two bodies moved. That repeated distortion revealed a companion. Once Charon was known, Pluto's mass could be calculated more accurately. Because the motion of the pair gave away the strength of their gravity, Pluto became smaller and lighter in human understanding. The lonely ninth planet became a double world. The name Charon reaches back to mythology, but the world itself is not shadow in the old human sense. It is grey, icy, fractured, and marked by a dark polar cap. Its surface is different from Pluto's in several important ways. It has far less nitrogen, methane, and carbon monoxide ice. Water ice dominates the crust, mixed in places with ammonia-bearing compounds and darker material. Without a thick blanket of volatile ices to flow and renew the ground, much of Charon appears older, harder, and more directly shaped by fractures and impacts. New Horizons approaches the Pluto system from one side only, and the encounter is fast. The spacecraft cannot linger. Still, during that short passage, Charon becomes a real landscape. The images show a world divided into regions with different histories. The northern hemisphere is rough and cratered. The southern plains are smoother, broader, and younger looking. Between them lies a system of cliffs, troughs, and canyons, so large that it seems to cut across the body like a frozen scar. One of the great features is Serenity Chasma, part of a larger belt of fractures that stretches across Charon's visible face. The chasm is hundreds of kilometers long and, in places, many kilometers deep. In the low sun angle of the images, its walls cast thick shadows, making the floor hard to see. The scale is not easy to hold in the mind. A canyon deeper than the Grand Canyon lies on a moon smaller than Earth's moon, in a place where the sun is a distant white point, and the ground is made of ice hard as rock. The canyon system suggests that Charon once expanded. That is the quiet clue written through the terrain. If Charon had an internal ocean early in its history, liquid water beneath an icy shell may have slowly frozen as the small world cooled. Water expands when it freezes. The growing ice would have pushed outward from within, stretching the crust until it cracked. The result would be a network of huge fractures, the surface splitting as the inside changed state. A world cooling in darkness can still break itself open. This idea gives Charon a hidden past. The surface seen today may be the outer shell of a body that once held more internal warmth. It may have had liquid water under ice when radioactive heat and leftover formation energy was stronger. As that heat faded, the ocean would freeze from the outside inward, changing volume, pressing against the crust, and leaving behind the long scars now visible from orbiting cameras and spacecraft images. Charon is not active in the same clear way Sputnik Planitia appears active on Pluto. Its story may be older. The movement may already be over. South of the Great Fractures lies Vulcan Planitia, a broad, smoother region that covers much of the visible lower hemisphere. Its surface is not perfectly flat, but compared with the rough northern terrain, it looks subdued, as if something once resurfaced it. The name suggests fire, but on Charon there is no molten rock flowing in red lines. If resurfacing happened here, it was colder. Slurries of water, ammonia, or other icy mixtures may have reached the surface long ago and spread before freezing. Cryovolcanism is a colder kind of volcanism, where the material that erupts is not lava but softened ice and chemical mixtures that can move under the right conditions. The evidence is not final. Vulcan Planitia may record cryovolcanic flows or some other broad resurfacing process. What matters for the journey is the possibility that Charon, like Pluto, was not simply abandoned to cold the moment it formed. Its interior may have separated into layers. Heat may have moved through it. Water may have changed phase. The crust may have broken. Smooth plains may have spread across older ground. Even in the outer dark, there is a difference between frozen and still. One feature in Vulcan Planitia draws the eye because of its shape. Kubrick Mons rises from the plain and appears surrounded by a moat-like depression. The mountain is not huge by planetary standards, but its setting is unusual. It looks almost as if a block of crust stands isolated inside a sunken ring. Some interpretations suggest it may relate to cryovolcanic activity or crustal movement. It could be a construct, a remnant, or a piece of terrain left behind as the surrounding surface changed. There is no need to force one answer. Charon has not yet been examined closely enough for certainty. The northern terrain tells another part of the story. It is more heavily cratered, meaning that it has carried its surface longer without being erased. Impact craters accumulate like marks on old skin. In the Kuiper Belt, bodies move slowly compared with the inner solar system. But collisions still happen across deep time. Small objects strike larger ones. Craters form, overlap, and remain unless some process covers them. On Charon, many craters remain visible. They show a surface that has spent a long time exposed to space. Near the North Pole lies the dark region called Mordor Macula. It is one of the clearest visual signatures of Charon, a reddish-brown cap spread across the pole. Its presence is tied to Pluto. This is one of the most delicate connections in the system. Methane, escaping from Pluto's thin atmosphere, can drift through space. Some of those molecules reach Charon and become trapped near its cold poles during long winters. There, ultraviolet light and charged particles alter the methane, slowly turning it into darker organic residues known as tholins. In that way, Pluto stains Charon. The process is slow, seasonal, and almost invisible at any given moment. Methane leaves one world, settles on another, changes under weak sunlight, and becomes a dark cap at the pole. The two bodies are linked not only by gravity but by chemistry. Material from Pluto crosses the distance between them and writes itself onto Charon's surface. It is not a large atmosphere shared by two worlds. It is a thin exchange, a faint transfer, a whisper of gas through space. Mordor Macula appears darkest near the pole and more diffuse around its edges, consistent with a process that depends on cold trapping and long exposure. As Charon's seasons change, different areas fall into long polar night or return to sunlight. Methane can settle, freeze, transform, and remain as residue even after more volatile material disappears. The reddish cap becomes a record of winter, radiation, and the slow loss of gas from Pluto. A color on the surface is also a history of motion. This makes Charon more than a companion body. It becomes a detector of Pluto's atmosphere, a place where escaped molecules leave evidence. Pluto's air is thin enough to feel almost not there. But Charon shows that it reaches outward. The system is small, yet it has weather of a kind that crosses between worlds. Not weather with wind and rain, but weather of sublimation, escape, cold trapping, and chemical darkening. In the outer solar system, even the idea of weather has to slow down. Charon's gravity is weak. A thrown stone would fall slowly compared with one on Earth. The horizon would sit close, because the world is small. The landscape would curve away sharply, although the black sky and fixed presence of Pluto would make scale hard to judge. There would be no sound carried through open air, no blue sky, no breeze, only the surface, the stars, and the large locked body overhead. The sun would illuminate everything faintly, not with warmth, but with enough light to cast shadows across fractures and crater rims. The lack of a meaningful atmosphere changes the look of the surface. On Earth, air softens distance. It scatters light, blues the horizon, and fills shadows with reflected color. On Charon, shadows fall hard. Edges are sharp. The boundary between sunlight and darkness is clean. Crater walls, canyon rims, and ridges stand under a sky that offers no haze to make them gentle. Yet the whole place is not bright. It is lit by a far sun, and the light has traveled for hours to reach the ice. The comparison with Pluto remains constant because the two worlds are so close. Pluto has mobile nitrogen plains, a layered haze, and volatile ices that migrate. Charon has a harder face, dominated by water, ice, fractures, and ancient resurfacing. Pluto feels more active at the surface now. Charon feels like a world whose strongest changes happened earlier, when its interior was warmer and its crust was under stress. One is pale and red and hazed. The other is grey and scarred, with a polar stain made partly from its neighbour's escaping air. Their difference may come from size and composition. Pluto is larger and can hold onto volatile ices more easily. Charon is smaller, with less ability to retain gases over time. Methane and nitrogen do not remain in the same way. They escape or are lost, leaving water, ice, and darker process material behind. The two bodies formed together or were joined by a major collision early in solar system history, but they did not evolve identically. Shared origin does not mean shared fate. The origin of the Pluto-Charon system is often linked to a giant impact. In this view, a large body struck early Pluto, and material thrown into orbit gathered to form Charon and perhaps the smaller moons. The idea resembles the leading explanation for Earth's moon, though the details are different. A collision in the outer solar system would not have looked like the hot, bright violence imagined for the inner planets. It would have involved icy and rocky bodies, cold materials, and slower conditions, but the consequences could still shape billions of years. Such an impact would explain why Charon is so large relative to Pluto. It would also help explain the smaller moons in the system: Styx, Nix, Kerberos, and Hydra. These small bodies orbit farther out, irregular and much smaller than Charon. They are not the focus of the scene, yet they complete the architecture. Around the central pair, the minor moons tumble in complex rotations, affected by the shifting gravity of Pluto and Charon together. The system is not a simple set of circles. It is a small gravitational family. The presence of those tiny moons also hints at the aftermath of formation. Debris may have spread into a disk and gathered into small objects. Over time, resonances and gravitational interactions settled the system into its current arrangement. From far away, it would look delicate. Two large, icy bodies locked face to face, and several small, dark fragments moving around them. All of it travels together around the Sun, far beyond the orbit of Neptune, in a region filled with other remnants from the beginning. Charon's surface preserves scale in a different way from Pluto's. Pluto shows active processes that may be ongoing, particularly in Sputnik Planitia. Charon shows old stress frozen into place. The cracks across its face are not just cracks. They are the memory of expansion, cooling, and perhaps the death of an internal ocean. The plains may be the memory of icy flows. The polar cap is the memory of molecules taken from Pluto and changed by light. The craters are the memory of impacts that were never erased. There is a quiet sadness in the fact that New Horizons saw Charon only once and from one passing path. The spacecraft gave a first portrait, not a full biography. One hemisphere is much better known than the other. Seasonal changes cannot be followed in detail. The chemistry of the surface can be inferred, but not touched. The depths of the canyons can be measured, but not entered. Charon is close to Pluto, yet still far from direct understanding. Future missions may return to the Pluto system one day. An orbiter could watch both worlds through changing seasons. It could map the far sides, measure the thin environment, study how material moves from Pluto to Charon, and examine the fracture belts with far better resolution. It could test whether Charon's plains truly formed from cryovolcanic flows. It could search for signs of past ocean chemistry frozen into the crust. For now, the system remains known through a single fast encounter and the patient work of interpreting it. That limited knowledge suits the place. The outer solar system does not give itself away quickly. It allows glimpses: a heart-shaped plain on Pluto, a dark cap on Charon, a canyon in low sunlight, a mountain inside a moat, a haze layer seen against the black. Each detail is clear enough to matter, but not enough to finish the story. The distance keeps some silence intact. Charon continues to face Pluto. Pluto continues to face Charon. Their locked hemispheres look across the same narrow gulf as the sun grows and fades over their long orbit. The smaller moons move outside them. The Kuiper Belt surrounds them with other cold bodies, many still unseen, many too small or too faint to have names. Together, Pluto and Charon mark the entrance to that region not as a lonely frontier, but as a pair of worlds bound by gravity, chemistry, and a shared beginning. Beyond their orbit lie other dwarf planets and planetesimals, dimmer to telescopes and less familiar to memory. Some are bright with methane frost. Some are red with old organic residue. Some are only dots moving slowly against stars. After Pluto and Charon, the path leads deeper into that belt, where the sun thins further and the surfaces become harder to read from Earth. The next world waits high above the main plane of the planets. Reddish and cold, with methane snow spread across a surface still mostly unseen. Beyond Pluto and Charon, the Kuiper Belt does not become empty. It becomes harder to see. The objects there are smaller, dimmer, and spread through a wide ring of darkness beyond Neptune, where sunlight arrives weak and scattered across frozen methane, water ice, and ancient dust. From Earth, most of these bodies are not landscapes. They are moving points. They cross the background stars so slowly that their motion has to be measured with patience, and even then they give away only fragments of themselves. Makemake is one of the brighter fragments. It moves far beyond Neptune, high above the main plane where the familiar planets travel, carrying a red surface through cold space. For many years, that tilt helped keep it hidden. Searches for distant worlds naturally looked close to the ecliptic, the broad, flat zone where most planets and many smaller bodies are found. Makemake was not there. It was lifted away from that crowded band, faint but large, waiting in a part of the sky where fewer eyes expected such a world to be. It was found in 2005, during the period when the outer solar system began to change shape in human understanding. Pluto was no longer alone. Eris, Haumea, Quaoar, Sedna, Makemake, and many others showed that the region beyond Neptune was not a final blank wall, but a crowded archive. Some objects were large enough to become round under their own gravity. Some had moons. Some had strange colors. Some moved in orbits that made the early solar system seem less orderly than old diagrams had suggested. Makemake belongs to that change. It is not as large as Pluto, but it is still one of the major known bodies in the Kuiper Belt. It takes more than 300 Earth years to complete one orbit around the Sun. Its path is not as stretched as Pluto's, but it is steeply inclined, tilted far from the plane of the planets. That orbital tilt gives it a quiet separateness. While Neptune and the other planets keep near the old flat road, Makemake moves above and below it, crossing the outer dark on a long slanted track. Its surface is bright, much brighter than many small objects in the same region. This brightness comes from frozen methane spread across the ground. Methane on Earth is a gas, invisible and light, something that belongs to atmospheres, lakes on Titan, and chemical reactions. On Makemake, methane is part of the surface. It freezes into solid grains under temperatures only a little above absolute zero. It can lie as frost, snow, or ice, mixed with ethane and traces of nitrogen, turning a distant body into a red-white world that no spacecraft has yet visited. The red color comes from time. Ultraviolet light from the sun is weak at that distance, but it never completely disappears. Cosmic rays and charged particles also reach the surface. Over millions and billions of years, they alter simple, carbon-rich ices. Methane and nitrogen are broken and recombined into heavier organic residues called tholins. These materials are not living, but they are complex chemistry, and they stain the ice with colors that range from amber to brownish red. Across the Kuiper Belt, red is often the color of exposure. Makemake's surface seems to hold large grains of methane ice. That detail matters because grain size changes the way light reflects. Fine frost can brighten a world like powder. Larger crystals can absorb and scatter light differently, making spectral fingerprints stronger or weaker. When telescopes study Makemake, they do not see its mountains or plains directly. They read the light that comes back. In that reflected light are clues about surface texture, chemical composition, and temperature. The world speaks in color and absorption lines. There is very little air there. For a long time, astronomers wondered whether Makemake might have a Pluto-like atmosphere that appears when it is nearer the sun and collapses when it moves farther away. In 2011, Makemake passed in front of a distant star from the viewpoint of Earth. Such an event is called a stellar occultation. The body blocks the star for a short time, and the way the starlight disappears and returns can reveal size, shape, and atmosphere. If Makemake had a substantial global atmosphere, the star's light would have faded gradually. Instead, it vanished sharply. That sharp disappearance suggested that Makemake does not have a thick Pluto-like atmosphere at present. If gas exists there, it is extremely thin, perhaps patchy, perhaps seasonal, perhaps limited to places where sunlight can warm volatile frost just enough to release molecules into space. Methane and nitrogen are always near the edge between solid and gas in these outer worlds. A small difference in sunlight can matter. A darker patch can warm more than a brighter one. A local deposit can breathe faintly, while the rest of the surface remains locked in ice. Makemake therefore feels both active and restrained. It has volatile ices like Pluto, but not Pluto's visible atmosphere. It is bright and red, but mostly unresolved. It has a moon, but the moon is small and dark. It is large enough to be one of the important dwarf planets, yet it remains mostly a disk of light to telescopes. It is known by measurement more than by image. Its landscapes have to be imagined from chemistry, brightness, and motion. The moon was found in images from the Hubble Space Telescope, a small dark companion now often called MK2. It reflects far less light than Makemake itself, which makes the pair unusual at first glance. A bright, icy primary with a much darker satellite moving near it. The difference may come from gravity. Makemake is large enough to keep methane frost on its surface over long spans of time. Its smaller moon is not. Methane once present there may have escaped into space, leaving behind a darker, older surface. That contrast is a quiet lesson in size. A world does not need to be much smaller before it loses the ability to hold certain ices. Gravity decides what can remain. Temperature decides what can move. Sunlight decides what can turn from ice into gas. Over time, two bodies born in the same region can come to look very different. One keeps a bright methane skin, the other becomes darker, stripped and bare by comparison. Makemake may have more complexity than current observations show. Some early data hinted at darker regions on its surface, perhaps patches where less frost is present, or places where older material shows through. Later observations made that picture less certain. The dark spots could have been measurement artifacts, or the effect of the small moon passing near the body in the line of sight. The surface may be more uniform than first thought, or it may still contain contrasts too subtle for present tools to resolve clearly. This is how much of the Kuiper Belt is known, partly, carefully, with room left open. A telescope sees a change in brightness. Another telescope records a spectrum. A star disappears behind an unseen disk. An orbit is calculated from years of positions. Each method adds a layer. None of them gives the feeling of standing over the terrain. Makemake remains a world of inferred frost, inferred dark patches, inferred seasonal gas, and a small moon whose orbit slowly improves estimates of mass. Still, the image that forms is strong. A red, bright dwarf planet travels in a tilted orbit beyond Neptune, its surface covered in methane, ice grains, and chemical residues, its air too thin to behave like Pluto's, its moon dark enough to almost vanish in the glare. It is not a dead pebble, it is a preserved experiment in cold chemistry. At that distance, the simplest molecules become minerals of the surface. The weak sun becomes a slow chemical lamp. Time becomes the main weather. Makemake also helps show why Pluto is not an exception. Pluto is better known because a spacecraft went there. Makemake is less known because no spacecraft has arrived. But both belong to the same broad population of icy bodies. Both carry volatile ices. Both show reddish tholins. Both have satellites. Both are part of the long story of material that never became a major planet. The difference is not importance. The difference is distance, timing, and the accident of which path a spacecraft could take. Far smaller bodies share the same region. Some are too faint to be more than numbers in a catalogue. Others have been seen closely only once. Among them is Arrokoth, the most distant object ever visited by a spacecraft. New Horizons reached it after Pluto, continuing outward through the Kuiper Belt until it passed a small contact binary in 2019. Arrokoth is not a dwarf planet. It is not round. It is a quiet, joined body, made of two lobes touching gently, like a pair of flattened worlds pressed together without violence. The close images of Arrokoth changed the mood of the Kuiper Belt. Here was not a large, active world with plains and mountains. Here was a small relic, reddish, smooth in places, lightly cratered, and strangely delicate. Its two lobes appear to have formed separately from a cloud of small particles, then come together at low speed, not smashed, not shattered, not melted, joined. The object seems to preserve a stage of planet formation before planets existed, when dust and ice gathered into larger pieces without yet becoming worlds. That makes Arrokoth precious in a different way from Pluto or Makemake. Large bodies change themselves, gravity compresses them. Heat separates rock from ice. Surfaces flow, crack, sublime, and renew. Small, cold bodies can remain closer to the beginning. Arrokoth is like a sentence from an older language, preserved because nothing strong enough came along to erase it. Its shape holds clues about how planetesimals formed in the outer solar nebula, the disk of gas and dust that surrounded the young sun. In older models, small bodies often grew through repeated collisions. Dust became pebbles. Pebbles struck other pebbles. Larger objects built up through impacts, some gentle, some destructive. Arrokoth suggests that at least some planetesimals may have formed by a quieter process, where local clouds of particles collapsed together under their own gravity. The lobes then met at low speed, more like settling than crashing. The result is a body that looks assembled by patience. There is no need for speed in this part of the solar system. Orbital periods are long. Sunlight is weak. Chemical change is slow. Even collisions can unfold differently when bodies move in similar paths. Arrokoth gives form to that slowness. It is small enough that its gravity is weak, yet strong enough to hold the joined lobes together. Its surface does not show heavy battering. It seems to have slept through much of solar system history. Exposed, but not transformed. Its red color again points to tholins and processed organic rich material. The same broad chemistry that tints Makemake also touches Arrokoth, though the bodies are vastly different in size. This repetition across scale is one of the quiet patterns of the Kuiper Belt. Large dwarf planets, small contact binaries, distant scattered objects, and cold moons can all carry reddish residues from radiation working on carbon-bearing ices. The chemistry is not dramatic. It is steady. It paints the outer solar system slowly. Makemake and Arrokoth therefore belong together in the same part of the journey, even though one is a dwarf planet and the other is a small ancient body. Makemake shows what happens when an outer object grows large enough to hold volatile frost and perhaps a faint seasonal atmosphere. Arrokoth shows what may remain when a small object changes almost not at all. One is a red icy world with a moon and a long tilted orbit. The other is a red double-lobed remnant, a piece of the construction material from which larger worlds were built. Between them is the broader truth of the Kuiper Belt. It is not merely a ring of debris. Debris sounds accidental, like fragments after something important has already happened. The Kuiper Belt is also a preserved reservoir. It contains pieces that escaped full assembly, pieces that remember the temperature and chemistry of the early solar nebula, pieces that were scattered, locked, tilted, reddened, frozen, and left in darkness. Some are large enough to have geology. Some are small enough to retain a primitive shape. Both kinds matter. The sun at Makemake is still present, but weakened. It can brighten methane frost and slowly drive chemistry, yet it cannot warm the surface in an Earth-like way. At Arrokoth, sunlight is even more like a suggestion than a force. At noon there would still be dim compared with daylight on Earth, though the sun would remain far brighter than any star. Shadows would be long and black. The surface would hold the cold without any air to soften it. Nothing would move quickly unless struck. The silence of these places is not empty silence. It is the silence of processes spread across ages. Methane grains forming and changing. Nitrogen refusing to stay where it is warm enough to escape. Tholins darkening frost one molecule at a time. A small moon losing its brighter surface. A contact binary carrying the shape of its birth. The events are too slow for ordinary attention, but they are not absent. The Kuiper Belt keeps working in its own time. From Earth, this work is studied through small changes in light. When Makemake rotates, its brightness may shift slightly. When a distant star passes behind it, the timing of disappearance reveals its outline. When Hubble or another telescope separates a tiny point from its glare, a moon is found. When New Horizons flies past Arrokoth, a body that had been a faint target becomes a place with shape, texture, and history. The outer solar system opens by increments. There is something calming in that method. No single observation explains everything. No single image finishes the story. Knowledge gathers the way frost gathers, thin layer after thin layer, until a world begins to appear. Makemake remains mostly unseen, but no longer unknown. Arrokoth is small, but it has altered the understanding of how early bodies joined. The Kuiper Belt, once a theoretical region, becomes a place of surfaces, colors, shapes, and slow chemistry. As the path continues outward, the objects grow stranger in their orbits. Some remain in the classical belt, moving on relatively stable paths beyond Neptune. Others have been disturbed, stretched into longer journeys, lifted into steeper inclinations, or pushed toward the scattered disk. The neat ring begins to blur. The solar system becomes less like a set of lanes and more like a field of old gravitational decisions. Neptune's influence is still present, even far away, written into resonances and tilts. Makemake moves within that outer order, bright and red, held in its long inclined orbit. Arrokoth drifts as a smaller memory of formation, its two lobes joined under a black sky. Behind them, Pluto and Charon continue their locked motion. Ahead lie bodies whose surfaces are colder, darker, and in some cases less stable. Some show signs of internal warmth where none seemed likely. Some carry crystalline ice that should not survive easily without renewal. Some have moons that help reveal mass and density. Each one adds another quiet exception. The next part of the journey moves toward two such bodies, Quaoar and Orcus. They are not as famous as Pluto, and not as visually known as Arrokoth, yet they hold some of the more puzzling evidence from the Kuiper Belt. Their surfaces suggest that even small cold worlds can preserve signs of change. Water ice appears in forms that point to renewal. Compounds may hint at buried chemistry. Moons travel beside them, measuring their hidden weight. In the darkness beyond Neptune, warmth does not vanish all at once. Sometimes it remains buried, faint, and difficult to prove. Quaoar moves through the Kuiper Belt with a quiet that can be mistaken for simplicity. It is far smaller than Pluto, too faint for the naked eye, and too distant for telescopes to turn it into a true landscape. For many years it was known mainly by its orbit and by the light reflected from its surface, a reddish object. A cold body beyond Neptune, a possible dwarf planet, moving through a part of the solar system where the sun is still present, but no longer familiar. Its path is more orderly than Sedna's and less zid-tilted than Makemake's. Quaoar belongs to the broad population of classical Kuiper Belt objects, bodies that remain beyond Neptune without being pulled into the more dramatic orbits of the scattered disk. It circles the sun in a long, slow year lasting almost 3 Earth centuries. During that time, the inner solar system completes countless seasons, civilizations rise and vanish, and Quaoar only continues along its wide, cold curve, turning under a black sky. The surface is red, like so many bodies in this region. That color comes from the same patient chemistry seen on Pluto, Makemake, and Arrokoth. Methane and other carbon-bearing ices are altered by weak ultraviolet light and by charged particles. Over time, they leave darker organic residues across the surface. The chemistry is slow enough to feel almost still, but it never fully stops. Even where sunlight is thin, time continues to work. Quaoar is not bright like Makemake. It reflects less of the sunlight that reaches it, giving the impression of an older or less volatile surface. Its gravity is weaker than Pluto's. Its ability to keep methane and other light compounds is limited. Molecules that rise from the surface can escape into space across long ages, slowly stripping the body of some of the more delicate materials that larger worlds can hold. Size decides what a world can keep, yet Quaoar is not only a dark red remnant. Spectral observations have found water ice on its surface, including crystalline water ice. That detail is quiet, but difficult. In the outer solar system, radiation tends to damage the orderly structure of crystalline ice over time, turning it toward a more disordered form. Crystalline ice therefore suggests that something may have renewed or exposed fresher material. The surface may have been altered by impacts. It may have been touched by internal heat in the past. It may have carried material upward from below. This is one of the first hints of hidden warmth. Quaoar is cold at the surface, so cold that common gases become ice, and the word weather has to be used carefully. But the surface does not always tell the whole story of an outer world. Inside a body made of rock and ice, radioactive elements can release heat over long periods. The heat may be faint. It may not be enough to sustain an ocean today. It may not even be enough to drive obvious activity now. Still, in earlier times, when the body was younger, that heat could have mattered. If icy material once moved upward from Quaoar's interior, it would not have erupted like lava on Earth. It would have been colder, slower, and more uncertain. Water mixed with ammonia or other compounds can remain mobile at temperatures where pure water would freeze hard. A slurry may rise through fractures, spread across a surface, and then freeze into a new skin. Later, radiation and micrometeorites begin their work again, darkening and roughening what was once fresh. The trace that remains is not a glowing flow, but a spectral fingerprint. There is another possibility. Impacts can also renew ice. A collision can excavate deeper material and scatter it across the surface. It can expose cleaner water ice that had been protected below. The Kuiper Belt is quieter than the inner solar system, but it is not free of collisions. Small bodies still strike larger ones across long spans of time. Each impact is a brief event inside a long silence, and its mark can survive because there is little atmosphere, no rain, no rivers, and no ordinary erosion to erase it. Quaoar also has a moon, Quaoar. This small companion helps reveal the mass of the system because its orbit responds to Quaoar's gravity. Without such moons, distant bodies are harder to weigh. A point of light gives brightness. A spectrum gives composition. An orbiting moon gives mass. From mass and size, density can be estimated, and density begins to suggest how much rock and how much ice a world may contain. Around small distant objects, a moon becomes a measuring instrument. Quaoar is much smaller than Quaoar. Irregular, or at least not clearly round, and dim. It circles the primary in the same outer cold, bound to a body that is itself only a faint object from Earth. The pair is not dramatic in appearance, but their motion carries information. Gravity, watched carefully over years, lets astronomers infer what the eye cannot see. In the Kuiper Belt, knowledge often arrives through patience rather than through images. Then, more recently, Quaoar became stranger. Observations of stellar occultations revealed a ring around it, a narrow and uneven band of material circling far from the body. The discovery was unexpected, not simply because rings around small distant bodies are hard to detect, but because this ring lies beyond the distance where ring material was expected to remain as a ring. In the usual picture, material outside a certain boundary should gather into a moon instead of staying spread out. Quaoar did not follow that expectation. That boundary is often called the Roche limit. It describes a distance inside which tidal forces from the central body can prevent loose material from clumping together into a moon. Rings around planets are commonly found inside such limits. Outside the limit, particles should more easily gather under their own gravity. Quaoar's ring sits beyond the classical version of that boundary. The ring should not be impossible, but it asks for a more careful explanation. The old rule was not wrong in every case. It was incomplete. The ring is not a bright band that a traveller would see glowing from far away like Saturn's rings. It is a subtle structure, found by watching starlight fade as Quaoar passed in front of a distant star. Brief dips in the star's brightness revealed material around the body. The event lasted only moments, but the timing carried shape. A world too distant for direct imaging suddenly showed that it had an outer structure, a fragile band of debris moving in the dark. This ring changes the feeling of Quaoar. It is no longer only a red icy body with a moon. It is a small system. Primary moon ring surface ice, old chemistry, and uncertain internal history. Each piece complicates the idea that the Kuiper Belt is made of simple leftovers. Leftovers can have architecture. They can have rings in unexpected places. They can preserve physical puzzles that force the rules made near larger planets to be tested in colder, smaller settings. The origin of Quaoar's ring is still being studied. It may involve collisions among small particles, resonances with Quaoar, unusual particle properties at low temperatures, or a balance between clumping and disruption not captured by simple models. The honest answer is that the ring is known, while its long-term survival is not yet fully understood. That kind of answer belongs naturally to the outer solar system. There, discovery often opens a door without lighting the entire room. Quaoar, therefore, stands at an interesting boundary. It is not as famous as Pluto. It is not as primitive-looking as Arrokoth. It is not as distant as Sedna. But it holds several quiet contradictions. Its surface is old and red, yet shows crystalline ice. It is small, yet has a moon. It is far from the sun, yet may have records of renewal. It should be simple, yet it has a ring where a ring was not expected to last. The world becomes more complex the longer it is observed. Farther along the same outer darkness is Orcus, another body that resists being reduced to a point in a catalogue. Orcus is a Plutino, meaning that it shares a 3-to-2 orbital resonance with Neptune, similar to Pluto. For every 3 orbits Neptune makes around the Sun, Orcus makes 2. This rhythm keeps the bodies from dangerous close encounters, despite paths that might otherwise seem linked. Neptune's gravity is not merely a disturbance. It is part of the pattern that allows Orcus to remain where it is. The orbit of Orcus resembles Pluto's in broad rhythm, but the world itself has a different tone. It is somewhat smaller than Pluto, with a surface that appears relatively neutral in color compared with many redder Kuiper Belt objects. Water ice is strongly present in its spectrum, and not only as a vague trace. Observations have shown crystalline water ice, and there are signs that ammonia-bearing compounds may also be present. Those clues matter because ammonia can change the freezing behavior of water and may point toward past internal chemistry. Again, the surface is cold. Nothing about Orcus looks warm in the ordinary sense. The sun is distant, the ground is hard. Volatile materials are limited, but crystalline water ice on such a body invites the same kind of question raised by Quaoar. How did ordered ice remain visible on a surface exposed to space radiation over billions of years? Some process may have refreshed it. Some process may have brought it up. Some process may have made the surface younger than it looks. Thermal models suggest that Orcus may once have had enough internal heat for partial melting deep inside. Long-lived radioactive elements in rocky material could warm the interior. If ammonia or related compounds were present, they could help liquid or softened mixtures persist at lower temperatures. A past cryovolcanic event may have carried crystalline water, ice, or ammonia-rich material toward the surface. The eruption, if it happened, would be ancient and cold, leaving no fire, only altered ice. The idea is not that Orcus is alive with activity now. The safer image is older. Orcus may be a world whose surface still remembers an internal event from deep time. A buried reservoir, a crack, a rise of softened ice, a freezing flow under faint sunlight, then billions of years of radiation, impacts, and darkness. In that sense, Orcus is not restless like Pluto's nitrogen plain. It is more like a cold page, with a few lines still legible from a warmer chapter. Its moon, Vanth, deepens the story. Vanth is large enough, compared with Orcus, to make the system important for measuring mass and understanding formation. The moon moves around Orcus in a relatively close orbit, and the two may be tidally connected in a slow gravitational relationship. Some studies suggest Orcus and Vanth could be locked or moving toward a locked state, though details depend on their masses, shapes, and internal structures. As with Pluto and Charon, a companion changes the primary. It gives rhythm to the system. Vanth is darker and redder than Orcus. That difference raises the question of origin. If Vanth formed from the same material as Orcus after an impact, their surfaces might be expected to resemble each other more closely, unless later processes changed them. If Vanth was captured from the Kuiper Belt, its different color would make sense. Though capture is not always easy to arrange dynamically, the system leaves both possibilities open. A moon can be a sibling, a fragment, or a stranger. The comparison with Pluto and Charon is tempting, but imperfect. Pluto and Charon form a large double system, with obvious surface exchange and a shared center of mass outside Pluto. Orcus and Vanth are smaller, darker, and less well seen. Their surfaces are known mostly through light, color, and spectral data. Yet the echo remains, a resonant outer body, a significant companion, water ice, possible cryovolcanism, and questions about formation. The Kuiper Belt repeats themes without making copies. Orcus also carries one of the more useful lessons for a sleep documentary about space. Distance does not always mean simplicity. It is easy to imagine that far worlds are frozen, finished, and empty of change. But every time they are studied more closely, some new layer appears. Pluto has moving nitrogen ice. Charon has giant fractures and a polar stain. Makemake has methane grains and a dark moon. Quaoar has crystalline ice and an unexpected ring. Orcus has water ice, possible ammonia chemistry, and a moon whose origin is uncertain. These are not dramatic changes in the human sense. They are not storms crossing a familiar sky. They are slower and more inward. Internal heat fades. Ice changes structure. Rings fail to become moons. Surfaces are refreshed and then darkened again. Molecules escape. Moons tug. Resonances hold. The outer solar system is a place where small forces, given enough time, become architecture. There is a gentle connection here to something more familiar. A frozen lake on Earth can look solid and still from above, while currents, pressure, cracks, and temperature gradients work inside it. The surface can hide the state below. The comparison is small, but useful. On these distant bodies, the ice shell is not a simple lid. It can be a record of the interior. A change beneath can appear later as a fracture, a bright patch, a crystalline signature, or a resurfaced plane. Quaoar and Orcus are especially valuable because they occupy the middle scale. They are not tiny, primitive objects like Arrokoth, and they are not as large and active as Pluto. They sit between those categories. Large enough to have gravity, moons, and possible internal processing, but small enough that every sign of activity is surprising. They show where the boundary between dead ice and geologic world becomes blurred. The word geologic also has to stretch out here. On Earth, geology is mountains rising, plates moving, rivers cutting valleys, magma cooling into rock. On Quaoar and Orcus, geology may be the slow creep of ice, the exposure of crystalline water, the survival of a ring, the freezing of an interior, or the chemical alteration of a surface under weak sunlight. It is geology at low temperature, geology without blue sky, geology that leaves thin clues instead of obvious monuments. A future spacecraft could change everything. A flyby of Quaoar might reveal whether its ring is narrow, clumpy, smooth, braided, or broken. It might show craters, plains, scarps, or fresh deposits on the red surface. It could measure Waywat more clearly and settle questions of mass and density. A mission to Orcus could map the relationship between water ice and darker terrain, examine Vanth separately, and search for the shapes that past cryovolcanism might have left behind. At present, these worlds are understood by methods that are powerful but distant. The distance is part of their character. They do not offer themselves as bright disks in the sky. They are inferred worlds. A spectrum here, a disappearing star there, a slow orbit around another faint point, a thermal model built from physical laws and limited measurements. The knowledge is real, but it arrives with edges unfilled. The mind has to move carefully through the gaps. That carefulness is not a weakness. It is part of honest astronomy. The outer solar system is not a stage built for clear answers. It is a cold archive with missing pages. Quaoar and Orcus are two of those pages, both partly legible, both marked by hints of warmth under cold. The warmth may be ancient, it may be faint, it may have lasted only long enough to change ice once and then disappear. Still, the surface remembers. Behind the path now lie Pluto's shifting plain, Charon's fractured crust, Makemake's red methane snow, Arrokoth's joined lobes, Quaoar's ring, and Orcus's possible buried chemistry. Ahead, the solar system begins to feel less like a belt and more like a borderland. The objects grow more scattered. Their orbits stretch farther from the sun. Some travel so far outward that they approach the region where the sun's authority becomes uncertain. The next world follows one of those long paths, red and cold, carrying its name from a goddess of the deep sea, moving towards sunlight only briefly before returning to the dark for thousands of years. Sedna does not belong comfortably to the familiar solar system. It is not close enough to Neptune to be easily shaped by that planet's gravity, and it is not far enough to sit plainly among the long-period comets of the distant Oort cloud. It moves between categories, through a borderland where the sun still holds it, but only across a distance so large that the hold begins to feel almost abstract. At first, Sedna was only a faint reddish point on images taken from Earth. It was discovered in 2003, during the same period when astronomers were beginning to realize how crowded and strange the space beyond Neptune truly was. The object moved slowly, but its orbit, once calculated, was not ordinary. It did not simply travel a little beyond Pluto, it followed a huge, elongated path, dipping inward only to a distance still far beyond Neptune, then climbing outward toward a darkness almost 1,000 times farther from the sun than Earth. Its closest approach to the sun is about 76 astronomical units. That is already more than twice Neptune's distance. Even at its warmest, Sedna never enters the main Kuiper Belt in the way Pluto does. Its farthest point lies hundreds upon hundreds of astronomical units away, in a region where the sun would no longer feel like the center of anything visible. One orbit takes roughly 11,400 Earth years. A single Sedna year is longer than recorded human history. That long orbit changes the meaning of time. When Sedna last came inward toward the sun, human beings were living near the end of the last ice age. Sea levels were lower. Coastlines were different. The night sky was familiar and unfamiliar at once, filled with the same stars but watched by people whose worlds were made of ice, stone, fire, and migration. Sedna has been moving outward and inward through one slow arc since then. Now it is approaching its closest region again. Not quickly, but by the standards of its own immense path. It will reach perihelion in the 21st century, though perihelion is a misleading word here. For most planets, closest approach to the sun means a stronger seasonal change, a more noticeable increase in light. For Sedna, the closest point is still deeply remote. The sun from its surface would not appear as a warm disk large enough to command the sky. It would look like an intensely bright star, sharper and stronger than the others, but still surrounded by blackness. Daylight there would be a thin idea. The surface is red, among the reddest known in the outer solar system. That color again suggests long exposure to radiation working on simple ices and carbon-bearing compounds. Methane, nitrogen, and other frozen materials may be present, but the exact mixture is still difficult to determine. Sedna is too far, too small, and too dim for easy study. Its spectrum gives clues, not a full inventory. The red surface may be coated with tholins and other radiation-processed material, an old chemical skin built slowly under a weak sun and a constant rain of energetic particles. Unlike Pluto, Sedna has no known large moon. That makes its mass difficult to measure. A moon would act like a balance scale, revealing the gravity of the primary through orbital motion. Without one, Sedna's density and internal structure remain uncertain. Its size can be estimated from brightness and thermal observations, but brightness depends on how reflective the surface is. A small bright body and a larger dark one can sometimes appear similar from far away. Sedna keeps part of itself hidden inside that ambiguity. The name fits the distance. Sedna is named after a sea goddess from Inuit tradition, associated with the deep and with creatures beneath the water. The astronomical body carries that name into a different kind of deep, not oceanic, but orbital. It is a red world moving through a cold outer sea of space, spending most of its existence far from the region where planets are easily seen. Its mythic name does not explain it, but it gives the object a feeling of depth that numbers alone cannot hold. Sedna's orbit is the real mystery. Neptune cannot easily account for it. The giant planet shapes many trans-Neptunian objects by scattering them outward, locking them into resonances, or stretching their paths. But Sedna never comes near enough to Neptune for that explanation to feel complete. Its perihelion is detached, lifted away from the region where Neptune dominates. Something else may have acted long ago. Something had to place Sedna on this distant path, or preserve it there after the early solar system changed. Several possibilities remain. A passing star may have come near the young sun while the solar system was still forming in a cluster of newborn stars. Such a passage could have tugged distant icy bodies into strange, elongated orbits. The sun itself may once have had closer stellar neighbors than it does now, and the outermost planetesimals may remember that crowded birth environment. Sedna's orbit, in this view, is not only a path through space, it is a fossil of the sun's earliest surroundings. Another possibility is that Sedna formed closer in and was lifted outward by the gravitational influence of an unseen planet. This idea leads toward the Planet 9 hypothesis, the suggestion that a large planet may still move far beyond Neptune, too distant and faint to have been directly observed. Such a body, if it exists, could help explain why some distant objects have unusual, clustered, or detached orbits. It would not be a replacement for Pluto. It would be something much farther out, colder, darker, and more difficult to find. The existence of Planet 9 remains theoretical. No telescope has confirmed it. Its proposed orbit, brightness, and position are uncertain, and alternative explanations remain possible. Some patterns in distant object orbits may come from observational bias, because surveys do not see the sky evenly. Some may come from the combined gravity of many smaller bodies, or from ancient stellar encounters, or from processes not yet fully understood. The honest state of the question is simple. Sedna's orbit is real. The cause is still open. That openness is valuable. It marks the place where the solar system stops feeling settled. The inner planets can be mapped, landed on, orbited, and photographed. The giant planets have been visited by spacecraft. Pluto has been seen in passing, but Sedna belongs to a region where almost everything is inferred. A handful of faint moving points can change the shape of the map. The border of the known solar system is not drawn by a wall, but by uncertainty. The Oort cloud lies beyond this, or is thought to. It has not been directly imaged as a cloud of objects. Its existence is inferred from long-period comets, bodies that fall inward from immense distances on paths suggesting a vast reservoir surrounding the sun. Unlike the Kuiper Belt, which is more like a broad, flattened ring, the Oort cloud is expected to be roughly spherical, extending in every direction, perhaps reaching partway toward nearby stars. Sedna does not sit fully inside that distant cloud, but it points toward it. For that reason, Sedna is often described as an inner Oort cloud candidate or a sednoid, one of a small class of objects with distant perihelia and huge orbits. These bodies are rare in current catalogues, not necessarily because they are rare in nature, but because they are so hard to find. Most spend nearly all their time far from the sun, moving slowly in faint light. They become easiest to detect only when they come closer to perihelion, and even then, close is a relative word. Imagine searching for a red-black ember in a field of stars. Except the ember is not glowing by its own light, and the field covers the whole sky. It reflects only the weak sunlight that reaches it, and it moves so slowly that its motion reveals itself only through careful comparison. Many Sedna-like objects could be out there now, near the far portions of their orbits, too dim for existing surveys. The present catalogue may be only the nearest edge of a much larger population. Sedna's surface temperature remains close to the bottom of ordinary planetary imagination. At such distances, the surface is only a few tens of degrees above absolute zero. Nitrogen, methane, and other volatile materials behave as hard frozen substances. A thin atmosphere may appear only faintly near perihelion if surface ice is warm enough to release a small amount of gas. Even then, the air would be far thinner than anything breathable, far more like a temporary exhalation of the surface than a stable sky. This gives Sedna a strange seasonal rhythm. For most of its orbit, it travels outward into increasing cold, and any faint gas collapses onto the ground. Frost settles, chemistry slows further. The sun fades until it is just one bright star among others. Then, over thousands of years, Sedna turns back. The sun grows slowly brighter. Some surface molecules may loosen. The world may form a faint temporary envelope, then lose it again as the long outward journey resumes. A season there is an age. If Pluto breathes over centuries, Sedna may breathe over millennia. The comparison is not exact, but it helps give scale. Pluto's atmosphere can change as its distance from the sun changes across a few human generations. Sedna's changes are spread so widely that no human project has yet watched even a small fraction of its full seasonal cycle. The object was discovered near the brief inward portion of its orbit. For almost all of its year, it would be much harder to see. Sedna may also hold clues in its rotation. Observations suggest a rotation period on the order of hours rather than many days, which weakened an early idea that a large unseen moon might be slowing it. Still, the absence of a known moon is not proof that none exists. A small or dark companion could remain hidden. But so far, Sedna appears solitary. It turns alone in the dark, carrying its red surface around under a sun too distant to soften the horizon. The interior is even less certain. A body of Sedna's size could contain rock mixed with water ice and other frozen compounds. Early in its history, radioactive heat may have warmed parts of the interior. Some models allow for the possibility that distant icy worlds can retain internal layers or past episodes of melting, especially if antifreeze compounds are present. But Sedna is so little studied that such ideas must remain careful. A hidden ocean is not known. A differentiated interior is not known. The surface offers hints, not answers. This caution matters because the outer solar system invites imagination. The distances are vast, the names are mythic, and the data are incomplete. It would be easy to fill the darkness too quickly. But Sedna's power comes partly from not being filled in. It is a measured object with an unmeasured story. Its orbit is precise enough to trouble old models, while its body remains vague enough to resist simple description. The result is not emptiness. It is restraint. There is a human connection in that restraint. Some places on Earth are known first by their boundaries. A coastline on a map, a dark shape in fog, a mountain seen from too far away. Details come later, if anyone returns. Sedna is like that on the scale of the solar system. Its orbit is the coastline. Its red color is the distant mountain shape. The rest is still fog. Near Sedna's distance, the sun's influence is not absent, but it competes with the wider galaxy in a way the inner planets never experience. Passing stars, galactic tides, and the ancient architecture of the solar birth cluster become more important at great distances. The farther an object travels from the Sun, the more vulnerable its orbit becomes to slow outside nudges. Sedna's path may therefore preserve a record not only of planets, but of the environment in which the Sun was born. That is a remarkable thought, but it should be held softly. The exact origin remains debated. A passing star, a rogue planet, a still hidden distant planet, or some combination of early processes may have shaped objects like Sedna. Each hypothesis explains part of the pattern. None has closed the case. Future sky surveys may find many more sednoids, and their orbits may reveal whether Sedna is a rare accident or one visible member of a hidden population. The Vera C. Rubin Observatory, with its wide and repeated survey of the sky, is expected to improve the census of distant solar system objects. It may not answer every question at once, but repeated deep imaging can reveal faint movers that older surveys missed. Each new distant object will add another orbit to the puzzle. A single unusual orbit can be mysterious. A group of them can become a map of unseen forces. Sedna waits for company. Until then, it remains one of the best symbols of the solar borderland. It is not the last object. It is not the farthest possible body bound to the Sun. It is not even the most distant object ever observed at a given moment, but it is one of the clearest signs that the outer solar system has structure beyond the Kuiper Belt. Its orbit stretches like a long thread from the near edge of darkness toward a region that has never been visited, never photographed as a whole, and never directly counted. Other objects have been seen at even greater current distances. Some small bodies, like Farfarut, have been observed farther from the Sun than Sedna is now. Long-period comets travel to still greater distances before returning after tens of thousands or even millions of years. But Sedna remains special because of its detached orbit. It does not merely wander far outward after being scattered close to Neptune. Its closest approach is already remote. It seems to belong to another layer. Layer by layer, the solar system changes from familiar to strange. The terrestrial planets orbit near the Sun, rocky and comparatively warm. The giant planets dominate the middle distances, surrounded by rings and moons. The Kuiper Belt holds icy remnants, dwarf planets, resonant bodies, and contact binaries. Beyond that, the scattered and detached objects stretch the map into long ellipses. Beyond them, the Oort cloud may form a loose sphere of comet nuclei reaching toward interstellar space. Sedna sits near the transition, red and slow. The name solar system can make all of this sound like a single, tidy structure. But it is more like a set of overlapping zones, shaped at different times by different forces. Close to the Sun, heat-sorted materials. Near the giant planets, gravity scattered and captured. Beyond Neptune, resonances and migrations left patterns in ice. Farther still, the galaxy itself may have touched the edges. Sedna is where those stories begin to overlap. No spacecraft is currently traveling to Sedna. Mission studies have considered the possibility, especially because Sedna is now moving toward the nearer part of its orbit. But such a journey would still be difficult. Even reaching Pluto required nearly a decade, with a fast spacecraft and a gravity assist from Jupiter. Sedna is much farther. A mission would need careful timing, high speed, long communication delays, and patience measured in decades. The object is close only in the language of its own orbit. If a spacecraft ever passed Sedna, the images might be quiet rather than spectacular in the usual sense. A red surface under a black sky, craters softened or sharpened by ancient processes, frost patterns from gases that appear only during long seasonal intervals, perhaps unexpected bright patches, perhaps a small moon, perhaps nothing that looks active at first glance. Yet, even a plain surface would matter. It would be the first close view of a world from the inner edge of the Oort cloud region, a place almost untouched by direct exploration. Until that happens, Sedna remains a lesson in humility. The solar system is not fully known simply because its major planets have names. There are bodies whose orbits take longer than civilizations. There are regions where sunlight becomes too weak to guide intuition. There may be unseen planets, or there may be no such planets. There may be thousands of detached icy worlds, or only a sparse population. The map is still being drawn at its outer edge. Sedna continues inward for now, though inward still means remote. It moves through the dark with a red surface, a long memory, and an orbit that points beyond the comfortable boundary of Neptune's reach. Behind it lie the brighter and better-known worlds of the Kuiper Belt. Ahead of it lies the larger uncertainty of the Sun's farthest domain. It does not answer the question of where the solar system ends. It makes the question quieter, wider, and harder to finish. From Sedna, the path can only go one of two ways. It can follow the Sun's gravity outward into the imagined cloud of comets, or it can turn away from the solar system altogether and look toward the nearest star. The next step does the second. After the red borderland of Sedna, distance changes its meaning again. The journey leaves behind worlds that orbit the Sun and begins to measure the gulf between suns, where Proxima Centauri waits as the closest star and still remains almost impossibly far. After Sedna, distance changes character. The outer solar system is vast, but it is still bound to the Sun. Pluto, Makemake, Quaoar, Orcus, Sedna, the scattered bodies, and the long-period comets all move within the same gravitational story. However faint the sunlight becomes, however long the orbit grows, the Sun remains the central weight. It holds them in curves that return. Beyond that, the darkness becomes interstellar. There are no more ordinary orbits around the Sun. There are no dwarf planets carrying frozen nitrogen across familiar years, no resonant bodies moving in Neptune's rhythm, no detached red worlds coming slowly back toward perihelion. There is only the gulf between stars, where the Sun becomes one star among many, and the nearest other light is still more than 4 light-years away. That nearest star is Proxima Centauri. It is not bright in Earth's sky. It cannot be seen with the unaided eye. Even though no known star lies closer to the Sun, it is too small and too dim, a red dwarf with a mass only a fraction of the Sun's and a light output far weaker. If Alpha Centauri A and B are the more sun-like members of the nearby triple system, Proxima is the small outer companion, faint, restless, and distant from the pair it belongs to. The word nearest can be misleading. Proxima Centauri is close only by the standards of the galaxy. Light itself takes more than 4 years to cross the distance. A signal leaving Earth during one season arrives there after years of winters, summers, and changed calendars. The space between is not filled with planets waiting one after another. It is mostly emptiness, dust grains, thin gas, magnetic fields, and darkness. The distance is so large that the human mind tends to shrink it into a phrase, the closest star. The phrase is accurate. It is also too small. Proxima is a red dwarf, a kind of star that is common throughout the Milky Way. Most stars are not like the Sun. They are smaller, cooler, and dimmer, burning their fuel slowly enough to last for immense spans of time. A red dwarf can remain on the main sequence for far longer than the current age of the universe. Proxima's faintness is not a sign of weakness in the long view. It is a sign of thrift. It spends its hydrogen slowly, yet Proxima is not calm. Red dwarfs often have strong magnetic activity, and Proxima is known for flares. Its surface can release sudden bursts of radiation, brightening the star and sending energetic particles into nearby space. For planets orbiting close to it, this matters deeply. A world can receive the right average amount of warmth and still be exposed to harsh stellar weather. Habitability is not only a question of distance, it is a question of atmosphere, magnetism, radiation, chemistry, and time. The first confirmed planet, Proxima Centauri b, was announced in 2016. It was not found by seeing the planet directly. It was found through the radial velocity method, by measuring the tiny motion of the star as the planet's gravity tugged it back and forth. The star does not sit perfectly still while the planet orbits. Both bodies move around a shared center of mass, and that motion shifts the star's light by a small amount. From that slight shifting, a planet can be inferred. Proxima b orbits very close to its star, much closer than Mercury orbits the Sun. Its year lasts only about 11 Earth days. Around a star like the Sun, such a tight orbit would mean furnace heat. Around Proxima, the star is dim enough that this close region may receive a level of energy that places the planet near the temperate zone, the region where liquid water could exist on the surface if other conditions are right. Those last words carry much of the truth. If other conditions are right, no one has seen an ocean on Proxima b, no one has measured a breathable atmosphere, no one knows whether the planet has air at all. The evidence shows a world with roughly Earth-like minimum mass, orbiting the closest star to the Sun, in a zone where surface liquid water is physically possible under suitable conditions. That is already enough to make it one of the most important exoplanets known. It is not enough to make it another Earth. The planet is likely tidally influenced by its star because it orbits so closely. It may keep one side facing Proxima for long periods, perhaps permanently, though the exact rotational state depends on its orbital history and internal dynamics. One hemisphere could receive the star's light again and again, while the other faces outward into darkness. Without an atmosphere, the contrast would be severe. With a thick enough atmosphere or ocean, heat could be carried from day side to night side, softening the difference. The surface climate depends on what surrounds the rock. This is where the flares return to the story. Proxima's activity may erode an atmosphere over time, especially on a close planet. Ultraviolet and X-ray radiation can heat upper atmospheric layers. Stellar particles can strip molecules away. A magnetic field might protect some of the atmosphere, but the presence and strength of such a field are unknown. A planet can sit in the habitable zone and still struggle to keep the conditions that make habitability meaningful. That point is easy to miss because the phrase habitable zone sounds generous. It sounds like a place already friendly. In astronomy, it is more modest. It describes a range of distances where the energy from the star could allow liquid water on a rocky surface, assuming the atmosphere is suitable. It does not promise water. It does not promise air. It does not promise stability. It only marks the place where one necessary condition might be met. Proxima b is therefore a lesson in caution. It is close, but unreachable by present spacecraft. It is temperate in a broad physical sense, but possibly battered by stellar activity. It is Earth-like in mass, but not known to be Earth-like in surface, sky, or history. It is the nearest world beyond the solar system that invites the strongest questions, and it answers almost none of them directly. That is not failure. That is what distance does. More recent measurements have refined the system. Proxima d, a much smaller planet, has been detected in a very short orbit close to the star. It has a minimum mass well below Earth's, making it one of the lightest planets found with the radial velocity method. Its year is only a little more than 5 Earth days. It is too close to Proxima to be considered temperate in the same way as Proxima b. It belongs to the inner heat of the system, where the star fills more of the sky, and radiation arrives with greater force. The detection of such a small world matters because it shows how sensitive modern instruments have become. A small planet pulls weakly on a star, and a low-mass star is itself active, noisy, and difficult to measure. Stellar flares, spots, magnetic cycles, and surface motions can mimic or obscure planetary signals. Finding Proxima d means separating the planetary rhythm from the star's own restless behavior. It is astronomy at the edge of precision, reading a planet from a movement smaller than the speed of a person walking. There was also a proposed outer planet, often called Proxima c, reported as a candidate on a much longer orbit. Its status has remained uncertain, and later analyses have not turned it into the same kind of firm world as Proxima b. The system is still being clarified. Some signals endure, some fade under better data. This is normal. Exoplanet discovery, especially around active stars, is not a single announcement carved in stone. It is a long process of measurement, correction, and return. Proxima's planets are close enough in cosmic terms that they feel almost reachable in imagination, but the physical distance remains enormous. New Horizons, the spacecraft that flew past Pluto, is one of the fastest objects ever launched from Earth. Yet, at its speed, a journey to Proxima would take tens of thousands of years. The problem is not knowing the direction. The problem is crossing the gulf. The nearest star sits beyond the practical reach of conventional flight. The emptiness between the Sun and Proxima is not completely empty. Interstellar space contains thin gas, dust, cosmic rays, and magnetic fields. A spacecraft moving through it at high speed would not pass through a perfect vacuum. Tiny dust grains could become dangerous at relativistic speeds. Navigation would have to be exact. Communication would be delayed by years. Power would be limited. Even a flyby would happen quickly after decades of travel, because slowing down at the destination is far harder than being accelerated away from Earth. Breakthrough Starshot was proposed as one possible path toward that problem. The idea is not to send a large spacecraft like the probes that visited the outer planets. It is to send tiny gram-scale nanocraft attached to thin reflective sails. A powerful laser array near Earth would push those sails with light, accelerating them to a significant fraction of the speed of light. If the concept could be made to work, such probes might reach the Alpha Centauri system in just over 20 years after launch, then send data home across the same 4-year gulf. The idea sounds simple only from a great distance. Each part is difficult. The sail would need to be extremely light and strong. The laser system would need enormous power and precision. The small craft would need to survive acceleration, interstellar dust, cold, radiation, and years of flight. It would need to aim well enough to pass near a target system after crossing trillions of kilometers. It would need to collect data during a rapid flyby and send a faint signal back to Earth using very limited energy. Nothing like this has been built for an interstellar mission. Starshot is a research program, not a launched spacecraft. Its value lies partly in the way it shows the scale of the challenge. To reach the nearest star within a human lifetime, a probe may have to become almost weightless compared with earlier spacecraft. The ambition is not only to go farther, but to rethink what a spacecraft is. Not a bus-sized machine carrying fuel and instruments, but a chip, a sail, and a beam of light. The contrast with the Kuiper Belt is sharp. Pluto required nearly 10 years for a flyby. Arrokoth required years more. Sedna would require far longer with ordinary methods. Yet all of those objects still belong to the Sun. Proxima Centauri is another star. The jump from the outer solar system to the nearest stellar neighbor is not a step of the same kind. It is a change of scale so large that even the fastest existing spacecraft becomes slow in a new way. There is also a deeper connection. The same outer solar system that seems remote from Earth is still the inner shore of the Sun's domain. The Kuiper Belt, scattered disk, heliosphere, and possible Oort cloud are not the end of distance. They are the gradual thinning of one star's environment before another star's environment begins. Proxima marks the next shore. Between the two lies the dark ocean of interstellar space. If a tiny probe ever reached the Proxima system, it would not enter orbit easily. At high speed, it would flash through the system in hours or less, depending on its path. Cameras and instruments would have only a brief window. A planet could pass through the field of view as a small disk, brighter than expected or darker than expected, perhaps showing clouds, perhaps showing none. Proxima itself would glare red nearby. The data would then take more than 4 years to return. The whole mission would be built around a moment. That moment, if it ever comes, would carry the weight of many older journeys. Telescopes turning toward faint points, photographic plates revealing Pluto, radio antennas receiving new horizons from beyond the giant planets, occultations tracing rings around Quaoar, radial velocity measurements finding Proxima b and Proxima d. Human knowledge of distant worlds often begins as a shift in light. Only later, sometimes much later, does it become an image. For now, Proxima b remains unphotographed as a world. It has not crossed in front of its star from Earth's point of view in a confirmed transit, which makes its radius and atmosphere harder to measure. Direct imaging is difficult because the planet is close to a star that, though dim by stellar standards, still overwhelms the reflected light of any nearby planet. Future telescopes may separate the light more cleanly. They may search for atmospheric gases, thermal patterns, or reflected colors. They may find signs of air or the absence of it. Both outcomes would matter. If Proxima b has an atmosphere, it would become a natural laboratory for understanding planets around red dwarfs, the most common stars in the galaxy. If it does not, that absence would also teach something, that close temperate planets around active red dwarfs may lose their air more easily than hoped. A barren result is still a result. It would shape the search for life elsewhere by showing where not to expect stability. This is the calm strength of astronomy. It does not need every nearby world to be welcoming. It needs them to be understood. A cold Pluto, a fractured Charon, a red Makemake, a ringed Quaoar, a distant Sedna, a flare-lit Proxima b. Each world expands the range of what a planet or planet-like body can be. Some are leftovers from formation, some are companions, some are possible ocean worlds, some are exposed rocks under active stars. The categories grow because the universe keeps refusing to be as narrow as the first maps. Proxima Centauri also reminds the journey that small stars matter. The galaxy is full of red dwarfs, and many of them appear to host planets. If planets around these stars can keep atmospheres, they may represent a large fraction of potentially temperate worlds in the Milky Way. If they cannot, then the habitable real estate of the galaxy becomes more limited in a different way. The nearest star system, therefore, becomes more than a destination. It becomes a test case. The test is not complete. Proxima b's atmosphere remains unknown. Proxima d's exact nature remains limited by the method of discovery. Proxima c remains uncertain. The flare environment is observed, but its long-term effect depends on planetary magnetic fields, atmospheric composition, and history. Models can explore possibilities, but models are not the world itself. The world is out there, moving around a small red star, receiving light and particles, keeping whatever surface it has in silence. From the perspective of the sleep journey, Proxima is not a place of arrival. It is a far lantern at the edge of possibility. After all the frozen bodies bound to the sun, after the red residues and nitrogen plains, after the hints of buried oceans and ancient rings, the nearest star appears not as a dramatic ending, but as a reminder that every edge opens onto another distance. The solar system is large enough to humble the mind. The space between stars is larger still. The sun, seen from Proxima, would be only another star in the sky, not the ruler of days, not the source of warmth, not the center of a familiar system, just a yellow-white point among many others. Around that point, unseen from so far away without instruments, Earth would move through its short year, and the distant icy bodies would continue their long arcs. Pluto would keep its heart-shaped plane, Charon would keep facing it, Sedna would keep traveling toward and away from the sun in silence. The journey has moved from the icy edge of the solar system to the first star beyond it, but the feeling is not of completion. It is of scale widening gently until the mind no longer needs to hold all of it. The outer worlds remain behind, still moving. Proxima remains ahead, still distant. Between them is the dark through which light itself travels for years. In that dark, the idea of a path becomes thin, almost weightless. Like a sail waiting for a beam that has not yet been built, the path grows quiet now. Far behind, the sun remains where it has always been, holding its small worlds in long curves of gravity and light. Far ahead, the nearest star still waits across years of darkness. Between them, the cold spaces widen without urgency, and nothing in that distance asks to be understood all at once. The outer dark can be left as it is, a field of faint light. A few red surfaces turning slowly. Ice that keeps old shapes. Thin sunlight touching frozen ground. And moving on. Somewhere, a small world continues along an orbit, so long that time itself seems to soften around it. Somewhere else, a companion remains fixed in another world's sky. Neither rising nor setting, only staying. The journey does not need a final border. The solar system fades rather than ends. One region becomes another. A belt becomes a scattered field. A field becomes a distant cloud, imagined from the paths of comets. Then even that begins to open into the space between stars, where light travels for years in silence before it reaches anything at all. Let the scale drift away now. Let the names become dim points. The cold plains, the red frost, the dark canyons, the thin haze, the small rings and hidden interiors can all recede together into a single calm distance. Nothing is lost there. It is only farther away. The room is close again. The dark is softer here. Breath settles into its own quiet rhythm, and the mind no longer has to follow every orbit. The stars can continue without being watched. The frozen worlds can keep moving in their patient paths. The night can hold all of it, gently, until thought becomes lighter and the last far light fades into sleep.